second lecture on Tuesday. So most of you probably know him as good in linear arithmetic, and not only linear arithmetic, but he's also good in other fields. He did a lot of nice research on automata logic, complexity, geometry, covering many fields. So currently he's a professor in Warwick, and the talk will be on one of these topics, namely mostly on automata with one counter. Dmitry, the floor is yours.
Thank you very much, Slavek, for the mic is off. It is green, so maybe I should stand here. No. I think there will be times I tend to move during when speaking, so I'm sorry. Well, I assume that the main thing will be the slides for which I thank my now former student Henry Sinclair Banks, who recently graduated and moved to the University of Warsaw in Poland. I also learned about half an hour ago that Nicolas Waldburger has also defended successfully his PhD thesis, and I've sent him an email asking what's next. So I don't know what the next or the current affiliation of Nicolas is. It certainly has been in Rennes. Yes, this is also joint work with Jérôme Leroux. And one more person to thank for on the slide is Masa Shirmohammadi from IRIF in Paris, without whom this work would not have been possible, and I'll mention that a little bit later. So what is this about? This is about one counter automata with some strange feature, or something maybe apparently strange feature, Disequality test, which I will explain in a minute. So let's start with one counter automata. This is a basic model of automata, and here I think the word automaton is a bit of a misnomer. I think it's certainly an automaton, but I think a more precise word would be one counter machines, because there are no input letters, there is no language accepted, it's just a program, basically, right? So here is an example of a one counter automaton. You can see that it has some control states, it has transitions, and transitions are labeled with integers. And the integers, their meaning is that this is an additive change, an update to the counter, right? So a configuration of such a device is a pair, the control state, so one of these S, A, B, C, D, T, and a non-negative integer. So the counter may not assume negative values, right? But also it has Disequality tests. So we can label control states with kind of extra conditions that forbid some individual configurations, right? So for example, if you are in control state B, you cannot be in configuration with counter value 15. So B15 is forbidden, right? So, and the way it works is just like that configuration is, well, stops being a configuration, or it's called invalid, right? So any run that we consider as valid should not contain any such configurations that are forbidden. So in this talk, the Disequality tests are shown on the control states, but actually it doesn't matter whether we decide to move them to transitions. It's like either choice is fine. But one important feature, both about the tests and about the updates, is that in this talk we'll think of them as relatively big numbers in the sense that they're written in binary, right? So if we look in comparison at counter automata, which are, let's say, if we view them as just special cases of push-down automata, where the push-down alphabet is a singleton, then the operation of push and the operation of pop is like plus or minus 1. Here we can do kind of a lot of pushes and a lot of pops at the same time, right? So this is binary. So this kind of tells us something about the complexity, right? So that's where we are. So as I said, I mean, just to kind of make this slightly more precise, what I said, and you can relax, is that the configuration is a pair. So here is a configuration B10. A run is a sequence of configurations. For example, we can go from S5 to B10 to C5 and then to T8. And the reachability question is the question whether there is a run from the initial configuration to the target configuration. So, well, if we start from S10 and end at T25, we can do something like 10, then we can go to 20, then it's 21. 21 is fine, it's not 15. 20 was also fine, it was not 26, right? So we satisfy all these disequality constraints on the way. So now we are 16, and this is not bad because we are kind of hold on. So we want to take the loop one more time because the total effect of this loop of the cycle was plus 10, plus 1, and minus 5. That's plus 6. So we would like to take this loop and kind of pump up. But unfortunately, we cannot take it more because 16 plus 10 is 26. So we can't take the transition anymore. And if you stare at this automaton for half a minute, you'll see that actually there is no other way to try to get to T. So in this instance, the answer to the reachability question is no. Okay. So that's that should in this model, there are no zero tests. It is possible to add zero tests to the model with a slight increase to complexity. As far as we know, maybe there is a way to actually get it further down. In most of the presentation, you can assume there are no zero tests.
Quality can be
That's a great question, and I'll answer this question in the second half of next slide. This is spot on. Yeah. Motivation. So why study this model? So this brings us to Ashwin's talk and the study of logic. So I'm not an expert on logic, so I know relatively little. So, but kind of when I read about this, people say that the question of reachability in one-counter automata or one-counter machines with these updates and these disequality tests is kind of eventually motivated by a model checking problem. So it's a model checking problem for machines with this one-counter and with these binary updates. But there are no disequality tests. Disequality tests kind of come from the logic. So people like Stéphane Dmitry and Arnaud Sangnier, and I think more people, have looked into a logic called flat freeze LTL. So it's flat fragment of something called freeze LTL. I cannot give you a definition of freeze LTL because I don't really know this definition, but the intuition is actually quite simple. So in freeze LTL, there is this kind of syntactic feature of the formula that's called the freeze quantifier. If essentially it allows you to kind of, when you're in the formula, to kind of, at some point, to pin down the current counter value. Then in other parts of your logical formula, of your LTL formula, you can kind of refer back to that counter value and say, oh, like I'm the same value, I'm not the same value. So you're kind of freezing a counter value, and then you're able to refer back to it, which is the freeze quantification. So if you do model checking of these kind of on these configuration graphs of these one-counter machines against that logic, then the problem that you're getting is essentially a version of this reachability problem with in these one-counter machines with these extra tests, right? So this disequality comes from these freeze tests. I think you actually may need there both equality tests and disequality tests, but we'll come to that in a second. So originally, the motivation for this problem was model checking flat freeze LTL on these one-counter machines. However, the complexity of that problem, of that model checking problem, was resolved independently. kind of people did not actually go through these automata in the end. So it was open for a while, but then people closed it by other means. But actually, I think there is a somewhat better even motivation, at least for me, for this model. This model with disequality tests, it kind of restores an important symmetry in these in this here. Let me explain what I mean. A different way, a different kind of place where one-counter machines arise is you try to model a variable and like software code, right? You write a snippet of code and there is some integer variable and then you can go up and can go down. It's a very simplistic model, but here is the thing. If you use this to kind of model actual code, of course, you can't do a lot of arithmetic and these things will be undecidable, right, rather quickly. But what kind of conditionals can you write? So if you just have kind of equality tests, that's kind of nice and, you can write some conditionals. Unfortunately, if you add, and I'll show this in a minute, if you add, look at these two lines, ignore everything else. If you add conditionals that say, oh, is it true that the variable is at most 25, right? These kind of tests. It turns out that the reachability problem for these one-counter machines, it becomes p-space complete. That's a result by John Fearnley and Marcin Jurczyński like 11 years ago. So kind of when you have these actual inequality tests like this, you can say, well, p-space is maybe not where you want to go, right? Let's say p-space is expensive. Tests that go at least are cheap. Well, they actually don't add much because if you want to test that your counter value is at least 42, what you do is you add two transitions. You first subtract 42 and then you add 42 back. Since your counter must be negative, that's for free basically. But these tests, they kind of increase complexity to p-space. However, and that's the previous citation here, if you only have equality tests, you can actually do it in NP. Right, so you can kind of reduce it to SAT solver. And actually people have reduced it to SAT solver and implemented that, and implemented even a bit more. But that kind of membership in MP is not a trivial result, because the thing is, yes, it is true that if the final configuration is reachable from the initial configuration, there is a run, and you can check if the run is valid. But it may well be the case that the run is exponentially long. I mean, it may certainly reach very high counter values. So somehow, what these people did, Hase, Kreutzer, Wagner, and Warrell in 2009, they found actually a succinct way to certify reachability. Right? It requires some work. I will not explain that in detail. I will say a few more words about that a bit later. But essentially, yes, for if you only have equality tests, the problem is in MP. If you have these kind of inequalities, maybe it becomes expensive. Okay, where is this disequality coming from? Well, here is the thing. Equality is good, but unfortunately, if you want to model code, it means that you can write if my counter value is 50, then something else, a conditional. But if you want to write the else branch of the same conditional, you actually need a disequality test. In some sense, this is a feature of this model of one-counter machines, of Minsky's model, right? Your conditionals are one-sided. You can have guards, you cannot say else. If you want to model the else branch, you need something like these disequality tests. And in this sense, the addition of this strange-looking feature restores symmetry in our modeling formalism. So I think that's a somewhat different and maybe better motivation. In general, you can ask a different question even. You can say, look, I have a model, in this case, it's, I don't know, this one-counter automata, and you say, okay, we have some framework in verification. Verification has acquired many ideas, techniques, and we kind of know how to solve a lot of problems. You change the problem slightly, you say, look, in the symphony configuration graph, let's forbid like these 5 configurations. Right? You cannot go through them. I mean, you would expect that you should be able to change your framework, your existing algorithms, slightly kind of put some little patches and your solution will work. And it's not clear if it does. Like people, I think, have tried to think about this problem, like what to do if you add these strange disequality tests. I mean, surely it couldn't be that much more difficult, but it seems to be elusive. I don't think there is an easy approach. So, what we've tried to do in this work is to kind of be in between this NP space to somehow go down to closer to NP. We didn't manage to get to NP. What I'm hoping to do in this talk is kind of share our thoughts and findings, and like how much we've managed to kind of to do here. So that's the motivation, and that's where this problem, admittedly a rather strange looking problem, is coming from. So we have these automata. They have these kind of disequality tests. They can be used arbitrarily. All the numbers are written in binary, and we're asking the reachability question. Okay. So in this long kind of introduction, I think I've probably bored most of you to death. So are there questions?
So given this motivation, instead of allowing this equality test everywhere and only allowing this structure, is it going to be any simpler?
It's a very good question, and I don't know. And thank you. So we can look into this. So, and I also remember now that I haven't answered Amal's question. So the answer is here. If you have a disequality test, you can kind of get rid of it, right? Suppose you say, oh, value 6 is forbidden, right? So what do? You take that transition, and then you say, well, I need to forbid 6. Okay, you write a transition that says, oh, what happens if my counter value is 0? It's a 0 test, and then I can continue. Okay, what if my counter value is 1? I need a different transition, a different test. It's also a 0 test or equality test, and I go on. And so on and so forth, up to 5. And then I can have a different transition that says, oh, let's subtract 7, and let's add 7 back. Right? If you do that, you certainly can pass the disequality test and vice versa. So this is good. Unfortunately, if you do that, you need to introduce essentially as many transitions or extra states as you had the value on the test as the guard.
As long as the value is in unary.
Absolutely. As long as the value is in unary, this is perfect. If the value is relatively big, in general it's written in binary, it explodes the configuration graph. So the problem is, of course, still decidable. It will be still in space, but yeah, the complexity, we don't know what to do with that kind of big machine. Yeah. So that is this one line that I didn't read. Thank you, Amal. More? Okay, good. So we're in between this NP space, and we're not completely sure where to go, up or down. So in the end, we managed to kind of go down in this complexity and kind of approach NP. The main contribution and some prior work. So as I said, NP hardness and NP completeness of the model with just equality tests. People have tried to solve the problem that we attack, and there has been some very good partial progress. So in particular, 4 years ago, this team of people from more than one place, more than, I don't know, maybe actually 5 different places, have managed to show that the coverability problem is actually in polynomial time. So the coverability problem just asks, instead of reaching the final configuration, can I reach the configuration with a particular control state? You can also say, or end at least this counter value, it's the same. You can, yeah. So it turns out that this is in polynomial time, and you should take my word for it. It's definitely not a trivial paper at all. This is, I wouldn't say ridiculously complicated, but it's really complicated. So somehow there is a lot of stuff going on. You need a lot of technology, and I'll show you some of that technology in one of the subsequent slides, because we need some of that. And also importantly, in our results, we rely on that procedure as well. Right? So in order for our results to work, you need some ideas and you need that polynomial time algorithm. If you don't have that, our result weakens a little bit, right? We still manage to get some progress, but that polynomial time helps a lot. Okay, so it's a very nice paper. So right, so this is the gap between NP and P space I was referring to. And what we managed to show is that actually the problem is in complexity class co-NP power NP. So I think it would be useful for me to know who is familiar with this kind of notation with co-NP power NP okay, so about half, good. So right, so I don't think that the exact definition will be like crucially important for the most of the presentation. So a 1 minute intuition is this. This says, so if you think of NP as a type of problem that you can give to a SAT solver and get an answer or hope to get an answer in some good time, then co-NP power NP is well, let's forget about the co. It's essentially a SAT solver that can ask a question of another SAT solver. Right? So why is that good? Why can a SAT solver be helped by another SAT solver? Because surely it should be able to resolve the problem itself. It's already solving SAT. So who knows the answer? It's a textbook computational complexity once you start doing oracles, which is not part of every computational complexity course, which means that I should explain this. So it's a strange and fun thing. The thing is, if you're a SAT solver and you're working on a SAT instance, and for some strange reason you want to ask a SAT query, if the actual answer to that SAT query is positive, it means that there was a certificate, right? You could have guessed the certificate yourself. You're solving SAT, right? That's the idea. However, if the answer to the actual query is negative, there is no certificate that you can guess. Well, not as far as we know, right? Like unsatisfiable CNFs may require like super long proofs. But in this model, when you have an oracle and then an oracle, that kind of upper oracle can say, well, the answer, that thing is unsat. And it may be useful for a SAT solver, well, for this bigger problem to know that. Right? So that kind of extra power is because we need to sometimes have more complicated assertions that require no. So that's why this thing kind of exists. Roughly speaking, I mean, a bigger view is that if you kind of start building these towers of classes, these classes kind of form something called the polynomial hierarchy or the polynomial time hierarchy. So so the bird's eye view is replace it in the polynomial hierarchy. So maybe coming back to Amal's question one more time, if you add equality tests as well here, you need to add, you go slightly higher in the hierarchy. You actually don't need to go to all the way to the third level. You go kind of level 2.5. I'll show this at the end. Okay, so that's the quick summary, okay, of what we do. Okay, I'd like to hope, well, I hope to share some ideas with you about how, what makes it possible. And I think there is some strange thing that maybe you should tell me about. Right, so what are we going to do? So roughly speaking, we would like to split the problem into several cases. So, and for some of the cases, we will mostly rely on existing work. And I'll kind of put some of that into assumptions or existing cases and won't talk too much about that. So let me write here. So my first assumption is that my automaton is strongly connected. Strongly connected. So let me say graph, which means that I'm ignoring all the labels. I'm just looking at the graph, and I want to assume that it's strongly connected. If it's not, it kind of introduces some extra levels of pain, and I will not tell you how to do that. If we have time at the end, I'll say a few words. So that's the first assumption, and that assumption is shown in red on the slides. Okay. So, and my second assumption will appear from this first case, and it kind of comes from, so let's say Px is my initial configuration and Qy is my target configuration, which is where I want to go. So my assumption, and that's what I would like to put here as item 2, is that Px, the initial configuration, can only reach finitely many other configurations. So, and what that case 1 does, it says, oh, suppose you can reach unboundedly many, meaning infinitely many configurations. Okay, so I'll show on the slide what happens if you can reach many, like infinitely many configurations. Suppose actually, let's assume two things here on the slide, that we can, not only we can reach infinitely many configurations from where we start, but also if you kind of look at the backwards direction, like look at the final thing and see from how many configurations can you reach the target, that is also infinitely many, right? So the initial configuration is unbounded, and moreover, the target configuration is unbounded in the reverse machine. Like what happens is that, right? That's our case 1. Well, it turns out that if that is the case, then it suffices to check the existence of a run in our machine, ignoring the non-negativity condition. This is what's called the Z run or integer run in the machine. And essentially it comes down to kind of to tracking the counter value, but kind of not thinking about all these inequalities that come from the kind of non-negativity constraints. So that is much simpler than usual reachability, and you can handle that. Intuitively, well, suppose you have a Z run from P to Q, right? So there is a way to get somehow, but you know, counter values can go up and down Z. If you are unbounded in the actual machine, it means that you can reach a positive cycle, meaning a cycle with a positive effect in total. Suppose you go to that P prime, right? And maybe there is this positive cycle. You can take that cycle, but also notice that you are strongly connected, right? We assumed in red that we are strongly connected. It means that from that kind of maybe higher configuration, I can go back to control state P. So I'm in a positive cycle, not just somewhere, but specifically I can have a positive cycle on P. Well, if you have that, that's great. Call it alpha. In the reverse automaton, I can do the symmetric thing, right? I can have, well, this cycle, and that's negative. Let's call it beta. So now what I can do is I can pump alpha many times, then I can take my integer run, then I can pump beta down. And what remains is, well, if I take this thing as many times as was the effect of alpha, and symmetrically, I'll match these things up. Okay, this might not suffice because there are disequality tests, but in that case, what I'll do is I'll pump it up even further up so that all the disequality tests are so far down that I don't even spot them, right? They're like. The only thing you need to do is you need to care about disequality tests like in the first iteration, but that you can handle that if you have the assumption that you are unboundedly many, right? So you can decide whether you can reach boundedly or unboundedly many configurations, and that is thanks to our friends from 2020 who solved that coverability question. So the test of whether the configuration is unbounded, that is due to them, right? So that's where they help. So therefore, if both of these things are unbounded, right? You're unbounded and you're reverse unbounded in the, you know, for the target, you're good, right? That's a good case. Therefore, either your initial configuration is bounded, or, well, your target configuration is bounded in the reversal machine, in which case you can kind of make it symmetric and assume that where you start from is bounded. So, right. So initial configuration can only reach, can only reach finitely many configurations. Right, so without loss of generality, we can assume that because there are some good procedures to handle the other cases. Okay, so case 1 on this slide is an MP, and that's your case 2, and that's what we'll focus on the slide. So that's the summary of that. If you didn't follow this bit, that's okay, because we just can make these 2 assumptions and go on. Okay, great. So where are we? So yeah, I'll hope to show that the case 2 is in this Oracle class. So we'd like to set something that will be an invariant for reachability. Well, the invariant will be for non-reachability. So that's a strange feature of our result. I actually cannot find, I don't know how to find a simple witness for reachability instances. I mean, usually reachability, you kind of find, maybe there is a run, maybe it's very long. You find a succinct way to represent the run. I don't have any idea how to represent this here. Like that was what kind of, without the disequality test, this is known. With the disequality test, I have no idea whether it's possible. What we do instead, we kind of look at instances where the answer is no, and we found a way to witness the fact that it's not, that the answer is actually no. So it's a form of invariant. And and what I'll show now is kind of what this invariant looks like. It'll take us more than one slide. So the first thing we'll do is for each control state in the automaton, we'll try to pick some kind of cycle that is based on that control state. And I'd like that cycle to have positive effect. It's possible to decide whether such a cycle exists. And such a cycle, I don't maybe, it doesn't matter too much which specific cycle we take as long as it's short enough, right? For each control state, I want to find some positive short cycle on that state, okay? So so here is an example. At P, the cycle has effect, what is it, +6, right? The cycle may have some drop, some demand on the cycle, right? I can't run the cycle if my counter value is less than 20. But also, if I start my counter, if I start my cycle at, let's say, 225, I cannot take the cycle either because of these tests, right? So, you cannot always take the cycle, but I pick some cycle. These cycles, I'm thinking of them as canonical cycles. They're kind of, we fix them once and for all, and, we'll use them throughout. Okay. So now, I said that the effect was 6. What this means is that all configurations, let's look at control state P. All configurations with control state P, I can split into 6 classes depending on the remainder modulo 6. Okay, so mod 1, 0, 1, 2, 3, 4, 5. Okay, so I'll kind of, on these kind of threads, lines, I'll kind of draw these configurations, denoting them by like points, right, visually. So I will have some black points. Black points are those that kind of configurations that are so low, I can't actually afford to take the cycle just because the cycle demands high counter value, right? So everything below 20 is kind of below that line, right? Kind of, yeah. So in principle, in everywhere above, I can afford the cycle, but it may be the case that I cannot actually execute it because of these disequality tests. So the first example is, well, if P150 is forbidden here, right? So it's on this one. But actually, as we saw, 225 is also not good. But 225 is like it here, right? Okay, so I'll show them as red forbidden configuration. So now, there are configurations that are above disequality tests, or like here where there are none, right? So these I'll show as green. So notice that if I happen to land in a green configuration, what I can do is I can take the cycle as many times as I want, which means that every green configuration is unbounded. So if you actually remember what I write here, we can only reach finitely many configurations. So green configurations are kind of not of interest to us anymore, right? So I can assume that we'll never see green. Right, so the interesting stuff is in between, right? So in between, there are these blue things. Kind of, we are bounded from above by the presence of some test, right? We can't go up indefinitely. But exactly which of the blue configurations we can reach, I don't know. And actually, I don't quite know. Maybe kind of among these black configurations, some of them I can reach and some of them I cannot. right? So the reachability set is going to be black and blue, but like what proportion of black and blue is, requires work. I don't know. Good. So, that's where we'd like to focus our efforts. All right. So there are two ingredients here. So one ingredient ignores blue and focuses on black. So like I'm below this water line, right? Like I'm underwater. So I won't be able, so suppose I'm only black, I'm not able ever to take a positive cycle. So it turns out that reachability kind of within this black region can be solved in MP. This is kind of this pessimistic mode where I won't see anything positive. So this can be solved by existing techniques from 15 years ago. So they go back even further to Anka Mushal, Helmut Seidel on kind of flows in graphs. So I won't discuss this in detail. What we'll need is, well, let me call it a pessimistic reachability lemma. Right? The lemma says the pessimistic reachability, meaning whether I can go from a configuration to another configuration, both of them are below the line, and all configurations on the run are below the line. Right? So for these configurations, I can solve the problem in MP. This for us is easy. So let me remark that this kind of pessimistic run may well see many control states. Right? It may be exponentially long, actually, because you see, kind of this 20 is actually a number written in binary. I mean, these runs can be very complicated, but we can solve that in MP. The second ingredient is we're looking at the blue stuff, right? The blue stuff is bounded chains, and well, the slides say bounded chains are upward closed, and I think a more precise thing to say is that the reachable configurations within bounded chains, the set of reachable configurations in blue, that is upward closed. That's actually very simple, right? Suppose you get to see one of these configurations that is blue. Of course, by taking the cycle, you can go up in that chain arbitrarily many times. That's exactly what that sentence says. So if R is reachable confs in bounded chains, I don't know, let's say R may look like, I don't know, 60, 66 up to 144, right? So this is somewhere here, right? You see, not all blue in this line, but kind of only upward part. And the same, I will see a pattern here. It may be the case that in one of these kind of chains, right, this ladder is empty, or this ladder can contain all of them, but essentially you take the smallest one that is reachable if it exists. So actually I can describe that very concisely. I will say my reachable set is going to be an arithmetic progression that begins at control state P and counter value 60, and has difference 6. So I go in steps of 6. And well, here this is one of possible representation. I say how many times I can take that. Right? So this basically needs to refer kind of implicitly to this disequality test. Right? So don't think too much about this 14. Here is another arithmetic progression. You start at 81. That's this remainder 3 mod 6. And I go again in steps of 6, and how many times I can do this, right? So this will have a very concise representation, but of course I don't know what this number is and what that number is. I know what is the difference because I know these canonical cycles, but like where these actual progressions start, and right, and I mean, of course they go all the way up to the end of the chain, and I can figure out, but where they start, I don't know. So that is going to be the shape of the reachability set within this blue region. Okay, great. So these are the two things, right? So firstly, in the black region, pessimistic stuff, I can solve in MP. In the blue region, bounded chains, I can have this kind of nice description, but I actually don't know good parts of the description, the important kind of parts. Yeah. All right. So and this brings us to invariance, and I would like to witness non-reachability. So let me formulate that as a theorem. So suppose I take one counter automaton with disequality tests that is strongly connected, my first assumption. Suppose I have initial configuration Px and final configuration Qy. And suppose that the initial configuration is bounded, meaning you can only reach finitely many configurations. That's my assumption 2. Yeah. So the theorem says that there is no run from Px to Qy if and only if there exists a set I, intuitively I stands for invariant, that satisfies three conditions. Okay, so before showing the conditions, let me recall the idea of an invariant on the, using red pen on the board. So, well, usually inductive invariants, right? You would like to satisfy three conditions. The first condition in red is that your initial configuration is in the set. Secondly, the configuration that you're kind of keen to avoid, the target configuration, is outside the set. So final is outside I. And thirdly, the set is inductive, meaning that if a configuration is in the set, then every possible successor is also in the set. So let me write this using the post notation. So the post is a set of all successors, right? So post of I is a subset of I. So post is one step, right? So as long as you know that one step keeps you in I, then you're good, right? So that's the standard kind of way of writing the inductive invariant. So, yeah, final is not in I, right? So the existence of such a set I witnesses that if I start in it, in every step, since I must stay in I by condition 3, there is no way I can get to final because final is outside the set. Okay, that's the idea of the invariant. Very good. More questions about this red summary? Okay, all good. So let's try to mimic this here using these ideas of chains and so on. So the first condition is that I want to guess a set, I, set of configurations. Firstly, the initial configuration is in the set, Px is in I. Secondly, my final configuration is in something else. So, and that requires a little story. So the problem is, these automata are complicated beasts, and you've seen all these chains, and it kind of looks a bit ugly. We don't have a good handle. If you look at just the set of all reachable configurations, in usual transition systems, of course, such a set forms an invariant, right? Like if the instance is a no instance. You would like to guess that set. But this set is going to be very hairy. I don't know how to represent the actual set of reachable configurations in this model. What we'll do instead is we'll try to represent kind of the core of that set, some kind of key configurations in that reachable set. And that key configurations, that core, that is going to be my set I, not this thing, right? I'm guessing some other set I. And that set, let me actually call this thing J. Well, let me call this thing J, just to eliminate some confusion. So here I will write J. So I can't guess this J. Instead, I'll guess the core of J, which I call I. Okay? So, and this set I, so look, the idea is J is something that I denote by post star minus of I. Okay, so so suppose I don't write the minus. So post star is the set of all configurations reachable from I. I mean, if I try to say that my invariant is like written like this, and I'm guessing I, I'm kind of doing something silly because I have no idea what this post star actually does. That's the whole point of the project. What I can do is I can use this restricted operator. Minus says pessimistic. This is pessimistic post star. So I look at configurations that start in I and take some pessimistic runs. Pessimistic means kind of this black region like below that line. In NP. Maybe I don't know, like this stuff, this set may be big, but the idea is that pessimistic post star is something that I can handle. So instead of guessing this J, I'm guessing kind of, I represent J like that, and I'm guessing I. And now my I will have a nice shape because, okay, now I want to say that the final configuration is outside the actual invariant. So instead of J, I write pessimistic post star. That's condition 2. Right? So far I've matched 1 and 2. So now I want to say that post of J happens to be in J. right? It remains in J. Okay, so the condition will look different, but let's look at the left-hand side. Okay, so this says reachable Y configurations and the drop of all cycle, pessimistic. That's what we said. Okay, so condition 3. Look at the left-hand side. The first thing says post of this pessimistic post star, right? So what the first thing says is, suppose I'm in this kind of J and I take one step. What I'd like to write, and I can just write this on the left, and on the right, I can write the same pessimistic post star. Right? So the third condition can say post of pessimistic post star of I is a subset of pessimistic post star of I. That will be a valid theorem. So that thing here that on the slides is a bit more involved. But you see, you just write down condition 3, where instead of J, you write pessimistic post star of I, and that is what you want. And this will solve the problem. It will give you slightly weaker complexity, but that's the idea. Right? So you just want to write down the definition of an inductive invariant, and you're guessing I, and your invariant is pessimistic post star. So what that thing says, that thing refines it slightly to fine-tune the complexity. What it does, it says, oh, take that post of pessimistic post star, and don't look at like all these pessimistic complicated regions you can reach. Only look at the stuff in bounded chains, the blue stuff. And it says, well, if you intersect with the blue stuff, this constant bounded chains, you can kind of decide quickly. That must be a subset of I. So that's just easier to check in terms of complexity. So what this says is like if you start, so if your I is kind of these arithmetic progressions, then it says if you start in an arithmetic progression, take one pessimistic run, you can do this in MP, take one extra step, the automaton is small, right? You can enumerate possible extra steps. Then look if the end result is in blue, that's intersection, you can decide that. Then you must end up in possibly some other arithmetic progression. That's the condition on the right. Arithmetic progressions, if you have them, you can kind of check them quickly, right? Because yeah. So that's the idea of the theorem. If you know what this oracle machines do, you can basically encode all of these 3 conditions in MP power NP, and this gives you non-reachability in that complexity class. So if target is not reachable from the initial one, then there is a set of arithmetic progressions. That's what I'm saying, right? You guess a concise description of the set, meaning for each progression you guess where it starts, right, and where it ends. The intention is that you would like to guess just the set of reachable configurations R that we saw in the previous slides, right? So if you guess that correctly, then you can check whether any of these conditions is violated. And this is in the right complexity class with the solvers, as we discussed. So that's how you prove this theorem. So once you have that theorem, you're good. And that theorem kind of follows from, well, it requires work, but it follows from the machinery that I showed previously. So that's the key slide. So Slavik is probably going to out in -3 minutes. So let me wrap up. So it means that under these assumptions, you can solve the problem nicely. It takes time to get rid of the assumptions. So this gives you eventually the right complexity. That's what you can find in the paper. If you add the quality tests, this gives you 1 extra level or 1/2 extra level. And that's it. Thank you.
Thank you very much. It was worth having this 3 minutes more. Questions?
So once you have a positive cycle, is it obvious that you will have a negative cycle? I mean, you just said that, sure, we can pump it up and then deflate it.
No, you're right. So the idea is that if you can have a positive cycle at the very beginning and a negative cycle at the end, then you can match things up and so on. Now, if that conjunction fails, it means that either there is no positive cycle at the beginning, you can only reach finitely many, in which case we're here, or if you flip the automaton, you'll be here again. Flip the automaton, reverse all transitions, flip the minus to plus and plus to minus, and then you'll be here again. That's the idea. Sorry, I assume that if I had said this shorter, it would have been clearer. Sorry.
I have a question, maybe one more. If you
Yeah, so you have this upper bound of like second level of polynomial hierarchy. Do you have like any ideas for lower bounds?
We tried. It's very difficult to encode things using these disequality tests. We have some things that you seemingly it's not clear like how to do using usual automata, but we have no idea really how to encode any hard problems using this business. Tricky. But it's a very, very good question.
What about counters?
It's a good question, like what conditions you'd like to add to remain decidable. Because
Disequality tests, right?
so two counters, yes, I see what you mean. So if you don't have equality tests whatsoever, so you have vector addition systems with some disequality tests. So this is decidable. You can use existing procedures to do that and some tricks to get rid of these equality tests. So this you can, it is decidable. The complexity, I don't know.
Yeah. Thank you. Let's thank the speaker once more.
Thank you.
And I guess it's time for lunch now, right?